Well, hello friends. Welcome back to Emulator Hacking. Today we are going to implement the original intent of the emulator, which was to build something like Valgrind for Serenity. So I want a tool that can detect use after free bugs, buffer overruns, things like that, and just like memory mistakes. And now that we have built a pretty decent x86 user space emulator, I figured we can start to do more like Valgrindy features. So today we'll add malloc and free tracking so that we can know which memory the emulated process is allocated, and then we can verify memory accesses against our understanding of the malloc heap to figure out if the program is using memory that was freed or not allocated in the first place. So let's try it. Now, the first thing that we're going to need is some way to intercept malloc and free. And since we don't use dynamic linking on Serenity yet because the feature is just not finished, we are going to have to hook into malloc itself. So my thinking is that we would just use some like harmless instructions at the end of a malloc. So here, right, after you malloc, we actually have this thing here where we register a performance event if we're doing malloc profiling. But in our case, we actually want something to happen sort of seamlessly. So I figured we could use like some harmless instructions that the emulator would recognize as malloc metadata, basically. Okay, so let's see which instructions we have. Oops. So obviously we have a whole bunch because this is x86, but we need something kind of harmless, like something that can execute on the, like if you're running the program normally, it would just execute and do nothing. But if we are in the emulator, we can catch this. So this one is pretty good. This is a SALC that's like set AL from the carry flag. It's an undocumented instruction. It's kind of unlikely to occur in normal execution, and it just updates the AL register with either with a 0 or 1 based on the current state of the carry flag. So I think that would be a good fit. So let's use that. So wait, what was that opcode? D6, right? So malloc. So here we would do something like, I mean, there's probably nicer ways to do this, but like, what if we just do something like this? Actually, I suspect that GCC is not going to compile that. Yeah, no such instruction. SALC. Well, I'm telling you there is such an instruction, dude. Just do what I say. All right. And then let's see, so we have some like metadata that we want to share. Maybe we should have like, can we make a macro for this? Or we could make a function that does this, like UE log. And we would log an event like, I mean, it's the same basic concept as here, right? So it's like, and very similar to this stuff. And maybe I should be a good boy and use reinterpret cast here too. So let's put that in a separate thing so that it becomes a bit manageable, because we're going to have to do this in a couple of places. So UE log event, we'll push this somewhere else eventually. Event type, and then we'll have like data 1, data 2, something like that. Okay, and then what we'll do here is I guess we can just like push it on the stack. Kind of harmless. So if we push, I don't know, EDX. Let's do EC. Wait, which registers are caller saved? I don't remember. Caller saved registers. A, D, and C. All right, so let's just use D and C. So we'll push ECX and EDX, and then we'll just pop them right back off the stack. So this will be harmless when we're executing, you know, on the host CPU. What am I missing? Missing a whole bunch of things. Oh, I'm escaping quotes here. Okay, and then this will have some inputs. So the C will be data 1. Actually, I guess we want to push 3 things. We want the event type, the data, and data. Okay, so let's just push 3 things then. Okay, so we have A is the event type, C is data 1, and D is data 2. Okay, and then I guess we don't have to define that right now. We can just say 1 for malloc and 2 for free or something like that. We'll put this up top for now. Okay, and then we'll do the same when you free. So let's see. So when you free something, that'll be 2, and it's a free of that pointer. And something like that. So maybe this is not like the perfect way of doing this, because like you could imagine that some program would have this instruction, but they certainly wouldn't do it twice in a row. So let's use that as our secret handshake for now. 2 SALC instructions in a row, and let's just verify that this code will execute fine if we're running it on the host. It should do effectively nothing, right? Although I guess we need to, since we're doing an SALC, we need to tell the compiler that we're clobbering the AL register, which I didn't do. And I think since we're mucking with the stack a little bit, we need to also clobber memory maybe. So let's just say that we clobbered memory and AL. Is that valid? No? EAX? Wait, is this not how you do that? That's how you do that one, right? But what if I clobbered EAX? As involatile as impossible constraint. Can I do this? There we go. All right, let's take a look at the generated code here. UI log event. So what that will do is that it will do 2 bad instructions and then push ACD, pop DCA, and then return. Yeah, so like these instructions are running on every malloc and free, and you can't tell the difference, right? It's not going to make any difference basically whatsoever. It's a little bit of pointless nonsense, which I think we can suffer having this little nonsense overhead for now, but in the future we'll replace this with a special version of malloc that we can, like, if we have dynamic linking, then we can like divert you to using a specialized malloc for memory debugging if we're running in this kind of scenario. But right now, since we can't redirect you to a different malloc, we have to do something. So we'll do this. Can I get those on the same line? Oh, okay, fine. Clang format has ideas about inline assembly. It looks kind of goofy, but whatever. So that seems fine. So now let's catch these in the SALC instruction, which we don't implement right now. So actually, if we try to run something right now, it should fail in SALC. So we'll run like bin ID, and it fails soft CPU 1537, which is right here. So it's trying to run the SALC instruction. So what we'll do here is, I mean, the first thing we should do is like implement the instruction the way that it's supposed to behave, which is set AL from the carry flag. I think it's like this. Anyway, and then we will have our secret handshake counter. So maybe like secret handshake state. And if you SALC, then we will, let's see, if secret handshake state, if it's 0, then we advance. Else if and secret handshake state. If it's 1, then I guess we should advance again. So as long as we're less than 2, we should advance. Else secret handshake state. If you're doing more than 2, we'll just turn off the secret handshake at that point, I guess. I don't know exactly. It's going to be a little bit silly, but let's try. So this thing can just be a thing like that. And then the other instruction that we were running, which was packing all the data, was push. So push 32-bit register, right? So push reg 32. So here, what we'll do is we'll check if secret handshake state is 2, then secret data 0 is going to be, we'll read the general purpose register specified, so like that, whatever register we're pushing. If it's 3, we'll store the next one. Okay, and then we'll also increment the secret handshake state in these cases. And here we will return it to 0. Okay, so the 3 pushes that follow a sequence of 2 D6 SALC instructions will be our secret way to communicate to the emulator something from the inside. Yeah, that'll work for now. I'm sure that we can come up with some better technique later, but right now this seems kind of reasonable. And secret data 3. Okay. And then I guess we should also sort of react to this at the end of the handshake. Maybe we should do this after the push takes effect. Did I do that for SALC? Yes. Okay. So what do we do? If you reach the end here, then we will say did receive secret data. Yeah, we'll just say that, and then we can handle that somewhere in a separate function. I think would be nice. Did receive secret data. All right. And then what will this look like? Maybe we'll just like put it on the debug output for now. Secret. And then we'll have, I guess we'll know if it's a malloc or free based on the number. And then we can even do this. If secret data 0 is 1, then debug printf malloc p u bytes, right? And that will be secret data 1 and 2. Maybe they were the other way around, actually. I don't remember. Damn it, were they the other way around? Size comes first for some reason. All right, well, whatever. So size is first. Oh, wait, no, that was correct. Okay. Free. And then, yeah, so the free, of course, doesn't include the size because that's not part of the free API. Else, you know what, let's like assert not reached if we get some message that we don't recognize, because then somebody is running our secret handshake without us knowing what's up. That would probably be an issue. All right, so let's run bin ID and look at that. It's a trace of all the malloc and free events inside. Very, very cool. So using these notifications here, we should be able to reconstruct all of the malloc heap. At least what we need to catch some bugs. So that's really good. One thing here that will be kind of a problem, or it will be limiting the capabilities of this thing, is that we're using the default malloc, which is very, very happy to reuse memory. And for optimal bug catching potential, it would be better if it didn't reuse addresses so soon, right? Because the longer an address remains unused, the higher the chance that you can get a use after free, right? Because if you reallocate something and reuse an address that you've used in the past, now even if you're accessing that data incorrectly, we won't have any way to know that that was a use after free, right? So that would be like another thing that we can improve greatly once we're able to substitute malloc instead of just tracing it. But that's like a nice thing to do in the future. Right now, we're just gonna live with the malloc that we have and try to make sense of it. So, and by the way, I should mention that like here, the intent here is not to build all of these capabilities into the emulator and then have them like on always. Rather, this I think this is like one thing that we can do with the emulator, and it's going to add like kind of a pretty serious performance cost. So this will be like an opt-in mechanism that you can use, and then I'm not really sure how we're gonna organize all this code later. Like probably this will become some kind of library, and then we can build like a memory debugger utility, and then we can have other kinds of utilities, and they just add their own instrumentation as needed, and we don't run a bunch of instrumentation that we don't need for the task at hand, basically. But all of that is problems for future us, and right now let's just make like some naive representation of these allocations. So let's see. I guess we can say, we can build this in a slightly generic way, so we can have something like if malloc tracer or something like that, emulator. Let's call the emulator, yeah. Did malloc CPU or target, that's a nice name for it, target did malloc. Secret data 2, that's the pointer, and secret data 1 is the size. Okay, so we'll put that there. We'll just comment that out for now. And emulator target did free m secret data 1. Okay. And then the emulator needs to have some kind of receivers for these things. So we'll say like target did malloc. Let's put a badge here so that nobody else thinks that they should be calling this. That wouldn't be right. So a flat pointer to the address and a size t for the size. And for free is just a flat pointer for the address. Okay. And then we can put this logic in emulator instead. And let's see what we do with this. I was thinking we could have something like a malloc tracer class. So malloc tracer. Something like that. Oh, and of course, malloc tracer. All right. So what goes into malloc tracer? I'm not sure yet. We'll figure it out. But my thinking was that we would have these guys just call the malloc tracer. So like if malloc tracer, let's do this out of line actually, but we'll put a malloc tracer here. So he will be an optionally present thing. Okay. And in emulator CPP, we'll just add these. Okay, and then they will, we'll just say malloc tracer did malloc address size. There we go. I'm not sure why I'm doing it this way, actually. This is like an kind of an unnecessary step. Because we can also just do like this, right? This makes more sense. Let's do it this way. So we'll expose the malloc tracer, and then we'll just yoink these and actually put them on malloc tracer. And we'll need some includes here, act types, batch, all right. And then we should probably keep track of all of these things. So right now I'm just going to be lazy and use a crappy data structure, which is something I like to do. But in the future, we should replace this with a nice data structure. But right now, we're going to go with crappy. So let's see, struct malloc allocation. And a malloc allocation will be a pointer address and a size, right? And then the idea here, of course, is that we'll just have a bunch of these sitting around in a famous vector. Allocations. Okay, so scanning this vector, I can already tell is going to suck, but it'll be okay for our needs today. I think we don't have to get fancy. As long as the API here is good, we can replace the data structure later, and it shouldn't be particularly tricky. So here's our thing, and malloc tracer did malloc and did free. All right. Okay, so when we malloc something, we can just add it to the allocations list. Append. There we go. And when you free something, we can remove it. We should do more sanity checks here, but right now we'll just do it this way. So return entry address equal to address. Okay. So there we have it. Now, soft CPU, we need to actually check here. So if emulator malloc tracer, oops. Yeah, so this is how we'll do it. Cool. And then, now that we have these, let's see that everything still just runs at least. This bookkeeping is not going to be particularly heavy. The heavy part comes in when we actually want to audit memory accesses, because now we're going to have to audit them not only against the MMU regions, but also against the malloc set. So yeah, no slowdown here whatsoever. Still works, that's good. Now let's see about read memory. So read memory calls into the MMU, and I'm thinking that one thing is that malloc uses mmap, but we don't necessarily know that a given block is a malloc block. That's something that we could potentially annotate as well to reduce the number of MMU regions that we actually need to perform the scan in. Right now, we'll just assume that any mmap region is a potential mmap area, or potential malloc area. So let's see. Unless it's file backed, of course. So let's give this thing a back pointer to the emulator first of all, because the fact that we can't reach the, oh wait, no, we can reach the emulator through a singleton getter, actually. So never mind. That's what we're doing right here. So targeted malloc. So when we read 8 here, let's see, if it's not file backed, maybe like we can add a check here, like is malloc, and then we'll add an imperfect is malloc check. And map region is malloc, and then here we'll just say like if not file backed, and then we'll put a fix me. We should somehow know which map regions are malloc blocks. Yeah. This will help performance. It's gonna work even without that, but if we can do this, then we will have less work to do. So it would be a nice optimization, but we're not gonna worry about it too much right now. This is obviously incomplete. Okay, so is malloc. Maybe we should call it something even better, like region is malloc block. Yeah. Or just is malloc block. Yeah, that's the nicest one. So what do we do here? We check emulator the malloc tracer. So if tracer tracer, so what do we say now? Like audit read, and then we want to say a few things. So we want to tell it, I guess we can use a badge so that it knows that it's coming from us, and we want to say how many bytes to audit, and then the offset, which is to give the full address, we need the base plus offset, the base of this region. Okay. Yeah, so it's a 1 byte, we'll put the size at the end. So that will be a good API. Audit read. Actually, I was thinking maybe it doesn't need a badge. Maybe it needs like something else. Maybe we should like say who's reading. You know what? Let's not worry about that right now. Let's just do it this way. Anyone can audit. And audit right. Okay. So in malloc tracer, what do we do with these guys? Actually, let's just add these to all of the different reads here. So in the 16-bit, it's a 2-byte read. Here is a 4-byte read. And here is a 1-byte write. 2-byte write. Probably templatize this code. So repetitive. Okay, so we've added all the audit calls. Now we just need to do something with them. Okay, so now we need to, actually when we free something, we shouldn't forget it. We should just find it and mark it as freed. now that I think about it. And then if you allocate something that we've freed in the past, then we would replace it. So when you free something, we shouldn't throw it away. Let's fix that up. So find, and that's not gonna work. Okay, so let's just do it this way. Allocation in allocations. If allocation address equal to address, then here we'll do the work and then return, and then we'll assert that we never get here. Okay, so what do we do to this allocation? We say allocation freed true. This is going to be cool. Freed false. And then of course we can keep track of more interesting stuff like stack traces when you allocated, stack trace when you freed, stuff like that. But right now we'll just keep track of whether it was freed or not. So let's see. Auto allocation is find allocation for address. Okay, and then we'll say if allocation, if no allocation, we'll say no malloc allocation for this address. Let's say invalid size byte read at no malloc allocation found. So this might have some false positives since we're doing this for all non-file backed mmaps. I just want to see that we can fire this at all. So let's see. And that's good, and then we'll just return, and then if we do find the allocation, if allocation is freed, if it's freed, we'll say use after free. Maybe we'll even colorize this. I don't know, just something. And there are more things that could go wrong. Like it could be like part valid access. So like you're reading 4 bytes near the end, but not past like the whole end. We'll see. Anyway. Then we'll do audit right. Right. Okay. Now we just need to invent find allocation. So malloc tracer, malloc allocation. Okay, and then for auto allocation in m allocations, if allocation address, if address is, you know what, let's make a contains address, return allocation, otherwise return a null footer. Okay. Bool contains flat putter address const. Oh, we need to you know what? Let me be a little bit unconventional and just say A. If return A is greater than or equal blah blah blah, and A is less than address plus size. Okay. Forgot to remove. Forgot to declare find allocation, I guess. That's my bad. Maybe we should call these mallocations. That'd be a cooler name. Mallocation. Mallocation. You can call them mallocations. Okay, yeah, that's kind of a cute name. I like it. So this is imperfect because if we reuse an address, we need to throw away the old one. So here we'll check existing mallocation is find mallocation for address. So if this address is inside any existing mallocation, then this is not perfect actually, but it will work though. Yes, because the malloc that we use, it uses chunk sizes, so it's never going to give out different sized chunks at the same address. There will always be a one-to-one relationship between an address and its size. So that helps us. So if we can find a mallocation for it, we can just forget it. So we'll assert that the existing mallocation is freed, and then we can assert that the existing mallocation size is the size that we have. So like that. And then all we really need to do now is just update the existing mallocation to say freed false and return. Okay, starting to feel like mallocation was a little bit of a silly word, but at the same time it's also a funny word. And malloc allocation is very, very much a mouthful. Maybe what these things really are like malloc chunks rather than malloc allocations. Okay, so that runs fine, but we still didn't actually instantiate the malloc tracer. So now that we go and actually do that, so in the constructor here, we will set up malloc tracer is make malloc tracer. Can we do that? Yes, we can. Okay, so now this should slow down a bit. Oh, here we go. All right. Oh, look at that. That's stupid. I thought I was using printf, but clearly I am not. So here, let's just force it to be hexadecimal, and we'll just say address like that. Like this. So I don't know what these accesses are, but we'll find out. But evidently it's like very upset about something, so it can't find a allocation for something. All right. I'm guessing that this is malloc zeroing out blocks. Interesting. And then we have an assertion failure. Yeah, fine. So let's see. I guess if we've never seen a allocation for a chunk, if we don't find a allocation, maybe we should just ignore that for now. Let's just ignore that case and focus on the use after free. So I want to see if we can catch a use after free. That would be the first goal here anyway. Okay, so that's crashing the audit, right? Oh yeah, right. Because that null check is kind of important. So yeah, so we'll skip over these for now, because we'll have to think of a way. Let's do this. We have to come up with a way to not complain about malloc like initializing its own data. I guess one way we could do that is we could have more secret instruction stuff that tells the emulator that, like, okay, so this malloc block is now initialized and you can start auditing it. And then we won't try to audit a malloc block before it's actually like fully constructed. So that might be a good thing to inform the emulator about. But right now, let's just not think about that too much, because I wanna use after free, man. So step one is make sure that it runs. That ran. We have a bunch of these. I find them suspicious. I don't think that this code is use after freeing, but at the same time, I'm not completely sure. So, hello? So that doesn't use after free. This thing supposedly does. This is suspicious. So let's see, what is that thing here? If existing allocation size is not size, I mean, actually, it could be rounded up. Like, we're rounding up the malloc things. So this thing here is not necessarily going to be the same, because we always round up to a multiple of something or whatever. We have these bucket sizes or chunk sizes, so we're just going to overwrite the size. That's okay. Because here we're like, this is finer than the malloc metadata, because malloc only knows, like, oh, I have 16 bytes here, but maybe the user only asks for 13. Well, the malloc tracer is going to keep track of that 13, even though the malloc itself rounds it to 16. So we'll be able to catch a mistake where you actually only access, like, index number 14 out of 13 allocated, even though malloc thinks that there are 16. So that will be an advantage that this thing has. Oops. And it's still very upset about something. Well, I guess one thing we can do here is we can... The sequence here, like, this feels like a memset or something. But one thing we can do is we can just dump a backtrace when this happens, right? That would be very interesting. So we'll just say emulator the dump backtrace. So this will become extremely noisy, but this is what we want. Also, we should maybe use a different color here. This color is a bit, it like collides with this thing. So let's use red. Red for use after free. because it's like a red event, right? It's a very bad thing. And oh my god, okay, the back traces show up on the printf output. I was not expecting that. Let's put those on the debugger output instead. I want them to be here so we can see them. All right, so check this out. Use after free. It's in free itself, dang it. Oh, it's free, like overwriting the freed memory. Oh, that's so funny. Okay, so check this out. This is free. So we're informing the emulator that this memory has been freed before we actually call free impl. And then free impl will do this thing here, right here. So if we're scrubbing, which is on by default, so then we just fill the free memory with the scrub byte, which is ed. And we do the same thing for new malloc allocations as well. We fill them with DC. So this is just like a little trick that allows us to spot kind of visually very quickly if some memory is like malloced or freed recently. And it just helps catch bugs many times. So the fix here, of course, is going to be to not notify the emulator about the memory being freed until after we've actually freed it. So we'll just reorganize that a little bit. I think that will be a lot better. And then here, in malloc itself, it thinks this memory is thinks the memory is free when it's scrubbing in malloc. So now it shouldn't complain about free, but it will instead complain about malloc, yeah. Blah, 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 blah. So we gotta do something about that. So, what do we do about that? I guess this is too late to inform the virtual machine. We need to inform him at an earlier stage. So, like right before we start scrubbing, actually. So here is where we scrub. So before we scrub, let's just log. And we can do the same thing when we scrub for free. So we do the notification before the scrub. Or in free's case, this is fine too. But in the case of malloc, like we have to tell the emulator that, oh, this memory is now used again. Otherwise, we get this. Okay, still whining. Still in malloc. It's a read this time. Wait, what? Create uninitialized is in malloc, and it's doing an invalid 4-byte read. A read? I feel like maybe this is free list traversal. Because it's going to have to traverse the free list in order to find a suitable chunked block. Because when you free a chunk in a chunk block, then it goes on the free list, and then like it can be either it can be an allocated chunk or it can be in the free list. And if it's in the free list, then it's actually a free list entry, which is a linked list. So I think this is a linked list traversal of the free list entries that we're seeing here. which is a bit tricky. So how do we inform the the emulator that it's okay to ignore these? Like, these are not a problem. One thing we could do is we could just ignore, not audit if we are in malloc. That would be one option. So, like, look at the stack, backtrace stack frame thingy, and then check if we are in malloc. Let's see if that remotely makes sense. There's probably a more elegant solution to this, but this will also work right now. So if our, we can just symbolicate like this, basically. So let's see. If symbol is malloc, wait, how do we do this? This is hard to see from here. This is a really weird place to see this. Let's see. Okay, wait, who calls audit read? It's the region. We ask for a malloc tracer. Okay, let's do this. If emulator should audit we'll just put like a little thing like this. Or wait, even better, is in malloc or free. Is in malloc or free. That seems okay. It's a little bit weird, but we'll take it. So bool is in malloc or free. Const dump. This is not going to be fast, but whatever. So then elf symbolicate current instruction pointer. If symbol, or like return symbol is one of malloc or free. Okay. Still very noisy, but we are in malloc here. Wait, so why are we logging this? Use after free. We should ignore both those. Suspicious. Does this thing not work? Let's see. Result. I'm suspicious of this thing. Debug printf symbol, or let's just print out the symbol. And the result. Because maybe there's some white space or something that I'm not thinking of. Or whatever, I don't know. Let's just see what's going on. Oh. Okay, thank you. Very informative. Maybe we should say static string last symbol. If last symbol is not symbol, then print last symbol is symbol. Alright, so then we only see if it changes at least. Because I'm not going to wait for a billion of these. Okay, so here, oh, the symbol is malloc plus the offset. Oh, that's annoying. All right. So starts with malloc or symbol starts with this. Can be so optimized. This is a very, very hackish way of doing this. So we're just tolerating this right now, but we're leaving huge performance gains on the table here for sure. Which is good because then we have something to do in the future. All right, so it completed. Takes about 1 second, a little 0.8, 0.9 seconds to run with the malloc tracing enabled. So let's create a program that use after freeze. So just call it useRafterFree.cpp. And I don't know why I started writing it in the terminal. Let me write it here instead. Malloc 17. And then we free foo. And then we access foo. And then we return 0. And then maybe we even, I don't know, we can copy something into it. Hello. I don't know how to write C. But I'm evidently doing it. Okay, so we free it, and then we will replace the else with x's after we freed it, and then I need string.h. And then we try to print it here, and we'll also print it after we've freed it. Okay, very cool. Have to rerun CMake. Okay. So that actually crashes here because our malloc is already quite aggressive about marking memory as inaccessible if it's a chunked block, but you free the last allocation in a chunk block. We don't give it back to the kernel, but we actually mark it as unusable. But we should be able to sidestep that by making 2 allocations like that. Because then they will come out of the same chunk block and, dang it, char bar, holy bar. Let me leak it. They should come out of the same chunk block and only one of them gets freed, so we will not mark the chunk block as protected. Okay, so that ran fine. Oh yeah, it's because it's ID. What am I even doing? It still crashes. Okay, I don't know why. Oh, maybe this gets optimized out, actually. Let me just look at what this actually compiles to. The first malloc gets compiled out. All right. Wait, how do you do this again? Is it like this? Yes, it's like this. So turn off the optimizations. Let me shoot myself in the foot, please. Yes, now it works. And we have some garbage there. That's fine. Maybe we should do this. Or, yeah, we'll do that. Yeah, remove the new line from the test string. I don't know why that seems so important. Okay, so this is a use after free, but it's letting us do it. Let's see. And look at that. It catches them, and it shows us the backtrace. Very, very cool. Dude, how cool is that? And then, yeah, so printf does a strlen, and then it says, oh, this is an audit read use after free, invalid 1 byte read. It catches everything, dude. That's so freaking cool. So now we could even add some more information here. So in the malloc tracer, maybe malloc tracer should really be called like malloc auditor or something like that. But tracer is probably fine too. I don't know. Anyway, so if it's free, let's tell you more about this, because we found an allocation. It's just that it's free. So we can put some more information here. Address is how many bytes into the free block. We'll say offset into allocation, bytes into freed block of size. Size. Okay, just updating all of them to say mallocation. Okay, and then the offset into the mallocation is it's the address minus the mallocation address. And we can do the same thing down here. So that'll be a start. Okay, so you see it's 2 bytes into free block of size 17. Super duper cool, dude. Super duper cool. Maybe we should make this output like this information here is so bloated, like the whole name. We can skip that by using debug printf. Ooh, and then we can do this Valgrind style things instead, where they show like the PID like this. This is gonna look cute. We'll store the PID somewhere. This is just a little cache here. Maybe the get PID syscall should cache. So let's see. U byte read at address P So that's as PID, size, address. Okay, this is gonna look sweet. Zoo, actually. And then comes the backtrace. Yeah, right. And we'll do the same thing here, except we'll just say right. And maybe we don't have to spell out use after. We can say use after free that way. I was just. Or we can also say UAF. Everybody knows that anyway. UAF. And let's make this thing also do the PID thing. Kind of stupid that now we have two of these, but whatever. I just want it to look neat. This is really just me doing like an homage to Valgrind, but it's nice. Oh, I should add more space to it. Oh, dude, I forgot something. So let's see, let's have maybe 3 spaces. Three spaces is fine. And here we need the PID. Oh, and we should do same thing that Valgrind does, like print out an empty new line. I guess before a problem, just so that we sort of get like these separate things. So it'll look very cool. Look at that shit. Dude, how cool is that? I love this so much. This is really sweet. Okay, I wonder if this works on anything else. Hello, right? Like it doesn't catch any bugs here, or with ID, or if we do something like, I don't know, hostgoogle.com. Well, it's a good thing that it doesn't catch any bugs. Just thinking, what could we run? Well, this will get more interesting as we add more utilities for sure. I mean, not add more utilities, like make more things compatible. All of these things need some amount of work before they will run in the emulator. Not all of the things, but let's try something like this. That worked. The Gron tool. This is a great tool, by the way. It's like a semi-faithful implementation of a tool by Tom Nom Nom, which is called Gron for greppable JSON. It just takes JSON input and then rewrites it in this like array or assignment format, and it's very grep friendly. So if you're like catting the CPU info and you're just interested in the stepping field, then you can grep like that, right? It's very cool. Anyway, total sidetrack. So what should we do now? Now that we can do this, I guess we should just do some commits and then be happy for today, because can't work forever every day. So I think we'll start with the CPU stuff. Let's see, what do we have here? So this is like the secret handshake stuff, which we'll call the tracer. I guess we should just commit all of the tracer stuff. Here are some white space changes that I guess we can include, whatever. They were not so bad. SALC. Okay. You know what, let's just go through these changes. Malloc tracer, fine. This thing, I'm just gonna turn it on by default for now, but in the future we'll want to make this an opt-in thing. But for now we'll leave it on since we're like developing it. Blah blah blah, malloc tracer, blah blah blah. The audit calls, very good. And oh, this is the malloc hacking. Okay, so let's leave that one alone and do that in a separate commit. So let's see. Oh, and we need these new files as well. So, user space emulator. Trace or keep track of malloc and free. Or catch UAF, catch use after free bugs by tracking malloc and free. It doesn't fit on the one line. Catch use after freeze. No, like that? Okay, that's fine. So, okay. This patch introduces a malloc tracer to the user space emulator. If this object is present on the emulator, we'll say it that way, it will be notified. It will be notified. It can be notified whenever the emulated program does a malloc or free. Actually, we actually kind of need this thing here for this to work, obviously, so we'll put it in a separate commit, but like it's not going to start working until we have that turned on. The notifications come in via a magic instruction sequence that we embed in the libc malloc and free functions. The sequence is SALC, push reg32, push reg32. The free registers will be interpreted. The data about the malloc free operation is in the 3 pushes. I guess we can say push. We can say it this way: times 3 pop reg3 32 times 3. something like that. This sequence is harmless. We make sure this is harmless when running natively. Okay. Memory accesses on mmap region now are then audited to see if they fall inside a known to be freed malloc chunk. If so, we complain loud and red in the debugger output. This is very, very cool. It's also a whole lot slower than before, since now we're auditing memory accesses against a new set of metadata. This will need to be optimized, and running in this mode should be opt-in. Perhaps even a separate program, etc. All right. Very, very cool. And then let's commit this. Although let's tweak that up a tiny little bit so it looks a bit nicer. UE log event. So let's just say send secret data to user space emulator. And let's just call these data 1, data 2, data 3. Three. Okay. And we should probably move this to its own header and so on. We could put this in serenity.h. Here, this probably would be fine. Or we can even just declare it here. So these would be something like that. Let's see, communicate, malloc, and free operations to user space emulator. Use the secret handshake mechanism, or secret messaging mechanism of user space emulator to sneaky SALC secret mechanism to inform it about malloc operations. Yes. That works. Use after free totally catches the things. All right. So this is going to be it for today's video. I'm really happy with the results, and I think this is just going to be so sweet. And obviously there's a lot more information we can add about these accesses and so on, but I just wanted to get to this point today, and we got there, so that's super cool. If you made it this far, then thank you for watching. I hope that you find this interesting. I certainly find it super interesting myself, because when I started this, I just had this vague idea of how to do it, and it seems to be working out beautifully, which is always nice. So yeah, thanks for hanging out, and I'll see you next time. Bye.